Welcome to Chapter 3, Lesson 2, or this is all about definite integral. So for today, our goals are, at the end of the lesson, you must have 1. Illustrate how to approximate the area of a region under a curve using the Riemann sums. Define the definite integrals as the limit of Riemann sums. Illustrate the fundamental theorem of calculus. Compute the definite integral of a function using the fundamental theorem of calculus. Illustrate the substitution rule. And compute the definite integral of a function using the substitution rule. First, what is the Riemann sum or Riemann sums? Now, generally, to approximate the area under a curve above the x-axis and bound by the interval a to b, we divide the interval into n number of rectangles and then find the summation of the areas of the rectangles. So in symbols, we write this down as the summation of f of x sub i's times delta x as I goes from 1 to n. So, the Riemann sum, in short, is simply an approximation of the actual area under the given curve. Now, take a look at this illustration. So, for example, we have this curve y equals 1 minus x squared. Now, if you use the Riemann sums, we simply divide the curve into various rectangles. So these rectangles must have equal width. So in this first illustration, okay, we don't have the rectangles yet. In the second illustration, we now have two equal width rectangles, okay. However, okay, if you can see here, there are some spaces, okay, in the rectangle which is not inside the curve. That means, okay, that means these spaces are not a part of the original curve, or this is not a part of the area of the original curve. This means that these spaces represent the error in the approximation. Now, if we try to make the rectangles instead of 2, let's say, let's divide that into 4 equal width rectangles. Now, if we have 4 rectangles here, okay, there are still some parts which are not inside the curve. So this is our curve, okay, above the x-axis, but between the interval 0 to 1, okay. So there are still some areas inside the rectangle, but outside the curve. Again, these represents the error in our approximation. Now, if we try to increase the number of rectangles that we have, okay, let's say we have a lot of rectangles now. Now, if you can see in the various illustrations, okay, if you increase the number of rectangles that you use to cover up the curve, the error in your approximation becomes less and less. So here we have lots of extra spaces. Here, the extra spaces has decreased. And in the third or in the last illustration, okay, so there is only a very small amount outside the curve. Now, take note, as the number of the rectangles increase, the approximation of the area under the curve approaches a certain value. Now, what is this value? We will soon find out. Now, how about the definite integral? So, if the function represented by f is continuous and non-negative on the closed interval a to b, the exact area of the region bound by the graph of the function f, the x-axis, and the lines x equals a and x equals b may be determined by taking the limit of the Riemann sum, okay, the one that we had earlier, as the number of n subintervals approaches infinity. Okay, so this exact area is denoted using the definite integral. So this is the symbol for the definite integral. So this is the integral of f of x dx from a to b. And therefore, since the definite integral is equal to the limit of the Riemann sum, okay, so this one is the Riemann sum that we had earlier. So take note that as the number of rectangles, which is represented by n, approaches infinity, okay, so the error in approximating the area under the curve becomes equal to the actual area, or the error becomes less and less such that there will be a time that there is no error anymore and the answer that you will get is the actual area under the curve. So this Riemann sum is now equal to the definite integral. So take note, the limit is called the definite integral of the function f from a to b. A here is called the lower limit of the integration, and b, okay, the other number in the integral, is called the upper limit of integration. Now take note, it is very important to note that definite and indefinite integrals are different. So indefinite integral is the one that we had in our previous lesson. Okay, if you want to know or if you want to review more on indefinite integrals, I will put the link below in the description box. So, take note, definite integral is a number, while the indefinite integral is a family of functions. So, another important concept that we need to understand is that here we have the parts of the definite integral. So, this one, okay, this long S sign is called the integral sign. A is the lower limit, b is the upper limit, f of x is the function or the integrand, dx, okay, refers or tells us that x is the variable of integration, okay, here. So we read this whole term as integral of f from a to b. So, now, one other important concept that we need to understand is that continuity implies integrability. So what does this mean? So if a function is continuous on the given closed interval ab, then the function is integrable on ab. Meaning, if the function is continuous on the given interval, therefore it follows that the integral of the function exists. Now, here are some of the most important concepts and properties that you must remember about definite integrals. So, we have two special definite integrals. First, so the function, which is defined at x equals a, then the integral of the function f of x dx from a to a is 0. So this means that if the lower limit is equal to the upper limit, therefore the integral of this given expression is 0. No need to solve. So whatever function that is, as long as the lower limit and the upper limit are equal, so Answer will be 0. Second, if the function is integrable or if the integral exists on AB, then integral of f of x dx from a to b is the same as the negative of the integral of f of x dx from b to a. In other words, if you interchange the lower and upper limit of the integral, your answer will be the negation or negative of your original answer. The next one is called the additive interval property. So according to the additive interval property, so for example, if we have this curve from the interval a to b and we have c, which is in the interval a to b, okay, and if the function is integrable on the given interval, okay, and c is in between, so the integral of the function from a to b is simply the sum of the integrals of the function from a to c plus integral of the function from c to b. So this means that if you get the integral from a to c and you add that to the integral from c to b, the answer will still be the same as getting the integral from a to b. So that's called the additive interval property. Next, we have the properties of definite integrals. So take note, if f and g are integrable functions on the given interval a to b, and k is a constant, then the functions k times f and f plus or minus g are integrable on the given interval a to b, and first, the integral of k times f of x dx from a to b is simply the same as multiplying k to the integral of f of x from a to b, and the integral of f of x plus or minus g of x from a to b is just the same as getting the integral of f of x, or the sum or difference of the integral of f of x dx and g of x dx from a to b. Lastly, we have what we call the fundamental theorem of calculus. So fundamental theorem of calculus tells us that if the function is continuous at every point in the interval a to b, and the function f, big F, is any antiderivative of the function f, small f, on the interval a to b, then the integral of f of x dx from a to b is simply f of b minus f of a, meaning this is connected with our substitution. So, to get the integral of the function f of x dx from a to b, we simply have to get the integral of the function, then substitute b minus integral of the function, then substitute a. Okay, so to illustrate this better and to understand this better, let us have some examples. First, we have the integral of 3 dx from 0 to 5. So take note, our interval here is 0, 5. So, to solve for the integral of 3 dx, so we simply get the integral of 3 using our various anti-differentiation rules. Again, we have learned the anti-differentiation rules in the previous lesson. I will mention the link of the video in our description box. So, we have integral of 3 dx is 3x, okay, using the constant rule. So, this time, since this is definite integral, we don't need to put plus c anymore. Okay, so that's 3x. So omit the plus c for definite integrals. You only use the plus c for indefinite integrals. So that's 3x, then that's from 0 to 5, meaning we substitute 5 first, minus we substitute 0. So that's 3x, substitute 5 first, that's 3 times 5, minus, substitute 0 here, that's 3 times 0. So 3 times 5 is 15, 3 times 0 is 0. So that's 15 minus 0, that is simply 15. So the integral of 3dx from 5 or from 0 to 5 is 15. Another example, we have the integral of 3x dx from 2 to 4. So again, we get the integral or anti-differentiation or antiderivative of 3x using our anti-differentiation rules. So that is 3x raised to 1 plus 1 over 1 plus 1 from 2 to 4. Again, no need to write plus c anymore. So simplify, that's 3x squared over 2 from 2 to 4. Again, we substitute the upper limit first, minus we substitute the lower limit. Okay, so that's substitute 4 first. That's 3 times 4 squared over 2 minus 3 times 2 squared over 2. So 4 squared is 16. So you have 3 times 16 divided by 2 minus 2 squared is 4. So that's 3 times 4 over 2. So 3 times 16, that's 48. So we have 48 over 2 minus 3 times 4, that's 12 divided by 2. So 48 over 2 is 24 minus 12 over 2 is 6. 24 minus 6 is 18. So the integral or the definite integral of 3x dx from 2 to 4 is 18. Next example, we have the integral of 4x dx from 1 to 2. So again, get the integral of 4x. So that is 4x raised to 1 plus 1 over 1 plus 1 from 1 to 2. So simplify, that's 4x squared over 2 from 1 to 2. Take note, we can cancel out 4 and 2. So this will give us 2 and this will give us 1. Simplify, this is 2x squared over 1 or simply 2x squared. That's from 1 to 2. Again, substitute 2 first minus the answer when you substitute 1. So 2x squared, that's 2 times 2 squared minus 2 times 1 squared. So 2 squared is 4, so that's why you have 2 times 4 minus 1 squared is 1, so you have 2 times 1. So 2 times 4 is 8 minus 2 times 1 is 2. So you have 8 minus 2, that will give you 6. So the integral of 4x dx from 1 to 2 is 6. And next we have the integral of 3x plus 4 dx from 0 to 4. So again, get the integral of 3x plus 4 dx. So that's 3x raised to 1 plus 1 over 1 plus 1 plus integral of 4 is 4x. Then lower and upper limit is 0 to 4. So simplify, that's 3x squared over 2 plus 4x. Again, we substitute 4 first minus the answer when we substitute 0. So that's 3 times 4 squared over 2 plus 4 times 4 minus 3 times 0 squared over 2 plus 4 times 0. So 4 squared is 16. Multiply that by 3 over 2. plus 4 times 4. Then we have 0 squared is simply 0. So we simplify. 3 times 16 is 48 over 2 plus 4 times 4, that's 16, minus 3 times 0 is 0 over 2 plus 4 times 0 is 0. Simplify. 48 over 2, that's 24, plus 16, minus 0 over 2, that's 0, plus 0, that's still 0. So 24 plus 16 is 40, minus 0, that's still 40. So definite integral of 3x plus 4 dx from 0 to 4 is 40. Okay? So, that is all for the lesson for today. For the next video and for the next lesson, you will know what is the application of definite integrals. Stay tuned for the next video. See you next time. Bye!